Okay, good morning, everyone. Yes, so this is the fourth lecture. So let me start with, so last time I hope people are not so tired of seeing so many inequalities and so on. But so let's do a recap and to remember what's our original goal. So this time I will do concrete examples to see that how the abstract machine we discussed last time, namely the Gorensky-McPherson inequality, and all, which are inequalities of the codimension bonds for the supports, and also the enhanced version for abelian, or weak abelian fibrations, namely the Ngo support theorem, and how they can be used to solve questions in concrete, in classical algebraic geometry and also in enumerative geometry. So let's focus on the example I mentioned at the beginning of the course. Of course, everything's over complex numbers. So we consider plane curves, so P2 and H to be, I denote by H the hyperplane class in P2, which are the standard, these are the standard notation. So to run these machines, the example we consider are the modular space of one-dimensional sheaves on surface. So we choose to consider modular space of one-dimensional sheaves just on P2. That's the simplest surface, compact surface. So this is the modular space of one-dimensional semi-stable sheaves in the sense of Yukinobu's lecture. But for P2, there's no choice of polarization, there's only one. And so I just omitted H semi-stable. So semi-stable, one-dimensional semi-stable sheaves, F, which I only, because we consider one-dimensional sheaves, so there's only two terms of the Hilbert polynomial, namely, I just read them concretely. One is the supporting cycle, the fitting support, which is basically remembering where the sheaf is supported on, which is degree D, this D. And the last term of the Hilbert polynomial, which is the Euler characteristic of this sheaf, I just remember it to be chi. So when you fix D and chi, you get a modular space. So this is a irreducible projective of dimension d squared plus 1. So the dimension actually is quite large in view of the degree. So there are two theorems I want to cover by the end of the lecture series. The first theorem is the cohomological chi-independence. So Yukinobu already mentioned this, the chi-independence phenomenon very briefly in his lectures. This is actually a phenomenon. I'll discuss more about it. So this is a phenomenon actually in enumerative geometry, in particular for the BPS invariants. But okay, so the good thing of choosing this example is that in this case, it is a complete classical statement. So it says the dimension of the intersection cohomology of this MD chi. So no matter which chi you choose, so this is, as a vector space, this is a chi-independent. Okay, so this will be covered by today. I'll explain how to deduce this from the Ngo support theorem. And then the next theorem, which we call cohomological stabilization, which says that, so now I'm using, after so 4 lectures and Camilla's exercise session, now I can state it in more precise form. So it says that the dimension, so that this group, MD chi, this is a Q vector space. So probably I need more space. Yeah, okay, let me try to finish this way. So this is equal to, I just give you a very precise formula. So this is the product. It's an infinite product formula, I. And you consider now in the denominator 1 minus q 2I plus 2, 1 minus q 2I plus 4. And you consider 1 over this person. So this is of course an infinite series in the variable q. And you then, so okay, you want to take the case cohomology, you just take the case coefficient of it. So you take the qk coefficient. So then this is true if k is not too large comparing to d. So so the k smaller or equal to 2d minus 4. So there's a linear bound on d. Okay, let's see what this the statement says. It says that if you want to consider the kth cohomology, then you can, first, the chi doesn't matter anyway by theorem A. And secondly, okay, the d matters, but when you increase d, then eventually d does not matter. For example, if the d is greater than 2d is greater than k plus 4, then it's the same number. It's always the same number. So this will be, theorem B will be proved tomorrow. Okay, so reference is actually, if you look at arXiv, for all the papers I co-authored, there's only one paper starting with, whose title starts with cohomological chi-independence. Also, there's only one paper whose title starts with cohomological stabilization, and these are the ones. Okay. All right, so any questions concerning the statement? Yes?
Sorry, what is the subscript qk?
So this is an infinite generating series, like 1 plus q plus q squared and with coefficients. And so if you want to consider the kth intersection cohomology, you just pick the qk coefficient of this huge generating series. That's it. So maybe yeah, thanks. qk coefficient. Yes?
So is there any reason why we write this way? Is it just a product of 1 minus q even power, just like everything twice except the first one?
This is a very good question. Yeah, well, okay, so you can also, of course, you can reorganize this, but the real formula we prove is not for actually intersection cohomology, for refined BPS invariants. So which basically is to refining the intersection cohomology by the perverse filtration, and then basically I would insert some numbers here, so the formula would be prettier. But yeah, it's not a very complicated formula. It's just like this. And the geometric reason hidden behind the right-hand side, as I stated in the lecture 1, is this side actually is relevant to the Hilbert schema points on P2. So yeah, thanks. Yeah.
Why does it depend on the d and the degree?
Oh, I will prove it. This. Yeah, for example, so the first statement is so let me make a comment. I will probably emphasize this later. So the theorem A is expected to be a complete general result for any Calabi-Yau 3. So for any Calabi-Yau 3-fold, if you do the BPS cohomology, then the chi-independence is, well, this is actually, I think, yeah, a version of it is conjectured by Yukinobu. But of course, not for the. So I don't know whether it is conjectured for the entire BPS cohomology, but at least for a specialization of it, which is the unrefined BPS invariants or unrefined Kuba-Kumova invariants. This is a general phenomenon, and this is actually relevant to the multiple cover formulas and the strong rationality of Donaldson-Thomas generating series. And for this part of the statement, which is the cohomological stabilization, actually I'm not sure whether this is a phenomenon for only for like Del Pezzo or Calabi-Yau 2 cases, or this is also a general phenomenon. For example, if you consider BPS cohomology for any x and beta curve class, then you can ask, so if you increase the curve class, like you can say beta 2, beta 3, beta, and so on, whether every BPS cohomology stabilizes. this is actually what Lucien asked at the lecture 1, and I don't have a bet even on whether this is the case. But so here we focus on the case of the Pezzo surfaces.
Do you expect it to generalize in the sense that K is a middle homological degree, like it's like d squared minus 1 by 2?
Well, the stabilization means, so if K is smaller than the 2D minus 4, this is true. Otherwise, this bound axis is sharp. So if you go beyond the 2D minus 4, then it's not exactly the right-hand side, but yeah, there are correction terms. So if, in particular, when you take K to be half of the d squared plus 2, this formula is not correct. It's only the stabilization result. Okay, so well, next time, tomorrow, I will talk more. I'll basically focus on this equation. But today, let's come back to the theorem A. So surprisingly, although theorem B is completely like a numerical statement, it calculates some invariants. But actually, we will see that both theorem A and B are just like direct consequences of support theorem. Okay, so some remarks. So first, okay, so maybe I write this way. So so today we will prove the theorem A in the following version. Oh. Okay. Yeah, thanks. Which I call theorem A prime. So the theorem A prime is the following. If we consider this MD chi, the modular space of one-dimensional sheaves, and this actually admits a fibration over some base B, which is the full linear system of degree D curves on P2. So this is a huge projective space. And the map is basically remembering where the sheaf is supported on. So you send F to the supporting cycle of F, which is a degree D curve, which might be very singular. So this is a proper morphism. And so the theorem A prime is that the support for the decomposition theorem of H is everything. It's just there's only one support, which is B. So okay, so remarks. So the first remark is that theorem A prime immediately implies theorem A. So in other words, theorem A is essentially a support theorem. So here's the reason. So we consider here B smooth to be the locus of smooth degree D curves. Which is a Zariski open subset sitting inside the entire B, for which we can consider the universal curve. So I'll call this P. So the P is the universal degree D smooth curves over some open subset of B smooth. And then the theorem A prime implies what? Implies if we consider the push forward, if you consider the decomposition theorem for the H, then it is full support. This means that everything are given, all the simple terms in the decomposition theorem are given by intermediate extensions of local system determined by B smooth. And over B smooth, every fiber actually is just the Jacobian variety associated with the degree D smooth curves, whose cohomology are completely given by the H1 of the corresponding smooth curve. So just writing down what I said, you got immediately that the decomposition theorem is I, and the IC, and B, and then the local system you put here are wedge I of the relative H1 of this P, which is R1 P lower star Q of this C. Okay, you just consider the variation of H1, and you shift it correctly, plus some constant, I don't know. Okay. So this is the local system computing relative H1. So H1 of smooth curves, whose wedge I will be the HI of the corresponding Jacobian. Okay, so in particular, so this is the way to see the chi independence. The left-hand side a priori depends on chi, but the right-hand side it does not. So the right-hand side is clearly chi independence. I defined what's the support of a morphism. This means that so if you consider decomposition theorem, it can be split into I, C, Z, some local system with some shift. And I collect all the possible Z, and these are defined to be the support sets, support set, sorry. And here, so this sentence exactly says that the B is the only support for the push forward of Q, which is exactly this sentence. Yeah, I defined this last time. Yeah.
Why is the local system given particularly? Because you are inducing it from the setting where you know the local system is given by that. I'm not sure why the local system is exactly of this form.
Oh, okay. So if you consider, so every fiber, in the smooth locus, every fiber is a Jacobian. So here you want to calculate the relative HI, and they are just given by the wedge I of the cohomology of the curve. Yeah. Actually, this is if you haven't verified this, this is an interesting statement to see. Yeah, this is actually a good question. So the right-hand side a priori, so since this is this is a family of Jacobians of the certain degree, which is given by chi, and so etalocally, if your family of curves has a section, then all the Jacobians are the same. So it's the same local system, but now so it's a simple exercise which you show that actually you glue these local systems. It turned out this does not depend on chi for the smooth curves. Because if you translate from one section to the other, this translation can be embedded to a smooth, can be embedded into a continuous group. So this X trivial cohomology. This requires some argument, but it's more or less obvious. Okay, so the theorem A prime is the one we want to prove today, and the second remark is, so for today, for convenience, we only treat the case where D is co-prime to chi, so that MD chi is smooth. If you look at the paper with Devesh, you see that Devesh Maulik, you see that this condition actually is not that essential. So the same argument I said today, after some generalization, will give you all the cases of D chi, all the cases of D and chi. But just for convenience, let me focus on the smooth case, since the ideas are the same. And the third remark is that in the co-prime case, so if you always assume that chi is independent of, is co-prime to D, then the cohomological chi independence was, before making this conjecture for P2, this was proved by Osu. Using scattering diagrams. It's a completely different argument. But the scattering diagrams, which might be relevant to his lectures last week here. I haven't watched through the lectures, but but the scattering diagram argument does not see, for example, the perverse filtrations, and also it's very hard to take care of the case for the general chi and d. Okay, so this is the overview of the main theorems we want to prove. So let me start with the technical part. So because we want to embed this story into the one I talked about yesterday, namely the consideration from the weak abelian fibration. So I think in today's exercise session of Camila's, probably she will discuss more about weak abelian fibrations. So recall that what is a weak abelian fibration? You have a morphism F, but there's an extra piece of data which will help you discrete the Gorensky-MacPherson inequality, which is a fiber-wise symmetry by some commutative group scheme. So so you want to find some P, connected commutative group scheme. So, okay, how do you find? So, the claim is that for the situation we're interested in, it is indeed the weak abelian fibration. But so let me just explain where you can find this P. So here the B in our case. So the B is just the full linear system. And now we consider not only the smooth curves, but the entire universal curve of a B. So for every point here, this grows out the corresponding degree D curve, which might be very singular. This is a universal curve over the linear system. And here, in this case, actually, the P is not hard. So you have a family of curves, and M parameterizes one-dimensional sheaves on those curves. One-dimensional sheaves on these curves, and the way that you can find the symmetry without changing the support and all the characteristic is that you consider line bundles, you tensor with line bundles, and that's what this P is. So the P is given by the neutral component of the relative Picard. So this is the identity component of the relative Picard. And then the action from P on M is also obvious. So you have a line bundle. You act on a one-dimensional sheaf, and the action is just given by tensor. You just tensor your one-dimensional sheaf with the corresponding line bundle, and then you get another one-dimensional sheaf, and you show that this is actually the stability condition is preserved, because the stability condition is a numerical condition.
The one-dimensional sheaves can have torsion?
No, it's the big stable ones.
It's stable.
Yeah. So, the M parameterizes stable one-dimensional sheaves, so it's pure one-dimensional sheaves. Yes, thanks. Okay. And the proposition is that MPB, so the modular space, the group scheme, which is the relative Picard, and the base, which is given by the full linear system, as above, is a weak abelian fibration. of relative dimension. So you can expect what's the relative dimension. So the relative dimension for general fiber, it will exactly be the Jacobian variety of a degree D curve, which by the genus formula, it would be that the corresponding Jacobi will have dimension D minus 1 minus times D minus 2 half. Okay, so this is not very hard theorem. So you basically you just check all the properties of the weak abelian fibration that so that these you check that these constructions satisfy that. So actually, when we were proving in this proposition, the hardest part is not that this is a weak abelian fibration, but that corresponding relative dimension. So we want to show that okay, so M to B has every fiber has this dimension. For the good fibers, it's very easy, and the task is to show that even for the worst fibers, which is very non-reduced and not irreducible, and still this is the bound. And this requires some work. Okay, so now, so this number is the arithmetic genus of a degree D curve. It requires an argument, but not very hard. Yeah. So the corresponding statement was first show, for example, when you run this argument for the Hitching system, that it's the same argument, essentially. Okay, so now let's prove the theorem A prime, namely the full support theorem for the supporting map. So the proof actually, the theorem is not a direct consequence of the Ngo support theorem. But there are two parts, which are of different flavors. The first part is to apply the Ngo support theorem to the large open subset, which is the integral locus. So integral curve. So we denote by B circle, B0 to be the locus of integral curves, which of course is a Zariski open subset of B. And then, so now we restrict our weak abelian fibration, so the M0 to be the pullback of the family over the integral locus. And then you can also restrict your group scheme over the integral locus where it's an action. This is the restriction. This is the restriction of the weak abelian fibration above to B circle. Okay, another data we discussed last time is the delta function. So for any point on the base, we have a delta function by calculating the affine part of the corresponding group scheme. So for here, you have a group scheme. For every point, you have a group scheme, which I call PB. And then the PB has an affine part and abelian variety part. So this delta only remembers the dimension, the complex dimension of the affine part of the group scheme. So this is a delta function from which we can define for delta z for any irreducible z inside B circle by picking a general point and consider the value of this function. Okay, these were introduced last time. So now let's see how they can fit into the pictures we consider for the concrete geometry. Okay, so the theorem 0, which is exactly the Ngo support theorem applied in this setting, which I hope everyone still remember the statement. So if we consider H circle going from M0 to B0, the integral part, if Z inside B0 is a support, then the inequality is that the codimension of this Z is bounded above by the delta function of this Z. And this is first part. And second part says when this is achieved, then the Z is detected by the top degree cohomology of the fibers. Okay, so we first explain why this is useful. Namely, Y theorem 0 will imply theorem A prime over the integral locus. So if you, okay, so we shrink, so we consider all curves, but we first through all those non-integral curves and just focus on the integral ones. Then I'm saying that the full support theorem is immediately a consequence of this. Okay, so theorem A prime over B0. The B0 is the Scuola set, which only considers dysmorphism. Yeah, but this is first step. So in the entire section here, the section 3, I'm talking about the integral part. Yeah. Okay, so this is actually this is immediate by combining with the inequality in classical geometry. So this is the Savary inequality. So this is an inequality from classical geometry of curves, which is of different flavors. So if you consider any family of, this is a family of integral locally planar curves. So you give some constriction the singularities of the singularities that can at worst be planar. If the relative compact by Jacobian is smooth, then for any irreducible Z inside B, sorry, it's a different notation, but I'm just, to avoid confusion, I'm just using B circle. Because we consider a family of integral locally planar curves. So for any Z in B circle irreducible, say, so we have the inequality of the other direction. So we know that delta Z, the delta function of any subvariety is bounded above by the codimension of Z. This has nothing to do with that Z is a support. It's just the smoothness of total family, and this tells you that this is true. So this looks like a quite surprising statement, but actually you just spell this out and see what this is saying. This says that, okay, so if you have a family of curves over some base, and generically, what it says that generically the delta has to be 0, because there should be no singularities of the curves. And in the codimension 1, generic point of codimension 1, the delta is at worst, if you want the total family to be smooth, the delta has to be at worst 1, at most 1. If generically in codimension 1 it's delta equal to 2, then this will break the smoothness of the total family. And so on. So this tells you delta is 0 at codimension 0, and is 1 in codimension 1, and so on. So meaning that when you go deeper and deeper in stratum, the delta cannot increase too fast. Otherwise, it will break the smoothness. Yeah.
Is there a theoretic interpretation to the affine part of the Jacobian?
Yeah, it's the model, the kernel. You know the abelian part, and then these are the line bundles which restrict 0 after pulling back to the normalization. Yeah. So if you consider a singular, for example, you consider integral singular curve, you take a normalization, and the map to the abelian part is basically the pullback of pull back the line bundle to the line bundle of the normalization. And the kernel is the affine part. Okay, so the last time I mentioned that this inequality is useful because most of the time you get inequality in the other direction, but now assume Z as support. The Engels theorem tells you that it has to be satisfied in equality in this direction, so to combine both two, now if Z appears to be a support, then this inequality is an equality, so the codimension Z combining both sides has to be. So this means that Z will be detected by top degree homology of the fibration, H0 M. Okay. This is the second part of the Engels support theorem. But on the other hand, there's no room for it because this sheaf actually is just circle. This sheaf is just a constant sheaf of the base. The reason is that it is calculating. So this sheaf, the top degree homology, is calculating the H top of the fibers of the base, and for any point in B0. And if you look at what this is you consider the integral curve given by B and consider all rank 1 torsion-free sheaves supported on it. And this is actually the classical competitive Jacobian of this integral curve, which you know it's irreducible. And then this is given by irreducibility. This is given by irreducibility. Of competitive Jacobians of integral curves.
So the rule that we are using, that if I have an integral curve, then any compact defined Jacobian would be isomorphic to the moduli of torsion-free sheaf. Is that?
That's the definition. So competitive Jacobian is the modular space of generically rank 1 torsion-free sheaves. And it contains the Jacobian which parameters line bundles and Zariski open subset. And in the integral situation where the singularities are planar, this is a dense Zariski open subset. So it's irreducible. In other words, if you consider the variation of top degree homology as a constant sheaf, there's only one component which does not vary. Okay, so then Engels support theorem tells you that if this inequality is an equality, then there should be the Z. If it's a support, then it will be there's some sheaf supported on Z, which will be a direct sum component of the R top H lower star Q. But then you know this is just a constant sheaf of rank 1, so there's no room for it. So in particular, then Z, the only possibility of the Z is just the entire B. Again, by part B of Engels support theorem. All right. Okay, so this is the explanation of the full support, how to see the full support property for the integral locus. But actually, you see immediately this argument fails if you want to go beyond B circle to B. Because if you consider H top of the preimage of B, where the B lies outside of the B circle, then the corresponding fiber would be highly non-integral. In particular, so the top degree, there were many components in the top degree cohomology. Certainly won't be a constant sheet for rank 1. So in other words, if you look at this invariant over the entire B, you're in trouble because there are too many candidates for the supports outside of B0. So I'm going there. Yeah. So the answer is yes, and it's even better. You can. So the idea is this is actually an observation by Chauduot and Lamont, who realized that. Yeah, let me just say it. So yeah, this is a very good question, and this is actually this depends highly on the so-called Del Pezzo or Fano condition for P2. So if you change the story at the beginning, you change the P2 by, for example, K3 surface, and consider one-dimensional sheaves there. Everything breaks down, and you will see the reason why it breaks down. 4, we go from B circle. So the first part actually does not depend so much on we're considering the pedal surface, for example, but the second part depends highly on that. Go from B circle to B. So the idea is to combine 3 things. Of course, the Ngo, the Savary inequality will be used. Ngo inequality will also be used, but you have an extra input, which is the Fano condition, which I will explain. What's the meaning of that? In here, of course, the final condition says that we're considering P2, but you will see where the final condition comes from. So combining these 3 ingredients, we can further squeeze the support, and by showing that there's no support in the complement of B circle. So first treat over B circle, there's nothing interesting happened. Well, nothing surprising happened, but then we try to rule out the possibility of extra ones beyond it. Okay, so to see how the final condition played a role, let's consider the following definition. So given D, we consider MD chi, which is the morphism from this to B, which is DH. And we define the phi D to be a function measuring the difference of the fiber and the base. This seems to be a very interesting, very funny thing to look at. So you consider, because this, so the fiber dimension only depends on D, not depend on chi. So we consider phi D to be dimension of a fiber minus the dimension of the base. And a priori, if you can mention that if the so the Ngo support theorem, or its original version, which is the Gorinsky-McPherson equality, tells you that so that the support, the codimension of support is dependent highly on the fiber dimension. So we put this as the invariant, and in the final condition, so this is measuring the size of the fiber minus fiber, size of the fiber minus the size of the base, to see how they are different. And in the case of P2, you can just calculate it. This is a linear function on D with a constant term 1. It's direct calculation. And the form why this, so you can define this function for any fibration, but it looks of this form is crucial for this purpose. Because if you can imagine, if you replace the P2 by K3 surface, then the kind of fibration would be Lagrangian fibrations. So this function will be 0 for any curve class. For the rest of the argument, you see that if it's 0, then everything breaks down. Okay, so let me make a comment here, which is that such invariant is 0 for Calabi-Yau-2 situations. Yeah. Yeah. Any dimensional, this will be 1 plus like canonical. So this -3 is the k beta intersecting with the canonical bundle. Yeah. Canonical divisor. Yes. And it works. So yeah. We'll see immediately what's the ingredient to make it works, which is this constant term 1, actually. Okay, so let's run the example. Let's run through the argument by actually an example. So let's assume C is a support. Now we consider the entire base B. So this is support. Such that, so let's assume by contradiction that you will have a support outside of the B circle. Then this means that a general point in Z won't be an integral curves. Well, we assume what it is. So just for convenience, let's consider the easiest case where to see how it works. So the general point in Z is of the form C1 intersect with C2. Let's just consider the simplest situation where you can have two curves. So this is our C. Okay, so it has to be the case. Otherwise, every support lies in the B circle. Okay, so here the assumption is the Ci integral. So a general point of Z is the curve such that it breaks into two parts. Each part is integral, and of degree di. Of course, the sum of these two is d. Okay, this is the toy model of the case where it breaks down, but the argument will be generalized to the complete general situation. So the claim, So the claim is that now I want to do the Savary inequality for this Z, whose generic point lies outside of B circle, of course. And as you expected, the classical Savary inequality tells you that it's bounded above by codimension of Z, which is the case where the Engels inequality is an equality. But where it breaks, then it will further have a correction term, which is given by this function phi d minus phi d1 minus phi d2. So this is the new multi-Savary inequality. And the reason it's even better is because now, by looking at the form of this phi d, this term is negative. So you have a leading term which is linearly dependent on d, so they cancel out. No matter how you split, it cancel out. But every time you split, these negative terms will contribute these constant terms, so that this term will always be negative as long as it splits. And this kills the entire story because the Engels support theorem tells you this will never happen because this has an upper bound which is given by this one. But you have this correction term, is this contradicting the claim. The claim contradicts and Gauss inequality directly. Even you don't have a chance that the inequality is an equality, which implies that no support lies in the B minus B circle. Okay, so in the last part, I will explain how to prove it. Yeah.
So in the case of K3,
Oy.
you have that this support could be outside the B circle, or
It happens. It does happen, and it's very complicated. And also the chi independent I stated is wrong. So the intersection. So you have to replace the intersection cohomology by BPS cohomology. And there are contributions from the smaller this. And but in view of the argument, you see what's happening. If you consider K3 surface, then this term is 0. So then, okay, you know that the inequality is equality, so you have to calculate top degree cohomology to see what kind of local system will contribute. And in the genus 2 divisibility 2 case, this was calculated by, for the intersection cohomology, this was calculated by the Cartado, Rabaneta, Saka, whose purpose is to calculate the Hodge numbers for the O'Grady 10 hyperkähler variety. And then using this calculation, the chi dependence was first proved by Sebastian, who verified the BPS cohomology version of the degree 2 K3 surface and the divisibility 2 case of the curve class. Yeah. And in this case, already you see that there are a lot of new supports which showed up. And the similar situation happened in the Hitching system case. Yeah. Okay, let me explain actually how to see this. Why the correction term is of this form. Since the idea of the argument is not so hard. And yeah. Okay, so now since we see that our curve C breaks into two curves, two integral curves C1 and C2, which is general. This is a general member in Z. Okay, so you want to calculate what's the delta function for this C. But it's hard because the delta function is the affine part, and the affine part depends on if you have two curves, they glue, and the gluing will affect the affine part. But on the other hand, you can look at the abelian part. So no matter how you glue, it will only contribute the affine part. So if you consider the peak 0 of C by looking at its abelian part, this will be just contributed by the abelian part of C1, abelian part of C2. There's no, how the glue will not affect the abelian part. Okay, so now let's just spell out the left-hand side. The left-hand side, so we will see from this equation actually how this phi d I defined, sorry, I just erased, how they contribute to both sides. So the left-hand side is, well, you take a dimension of a fiber, which is the dimension of M minus the dimension of the base. So this is a dimension of a fiber, and then you minus the delta Z, right? Because we consider a affine part. So we just take the total dimension of the fiber, and then you remove the affine part. That's tautologically, that's the abelian part dimension. Okay, so let me rewrite it. Dimension M minus, this is fiber dimension, so this is phi d plus dimension of base minus delta Z. Okay, well, let's evaluate the right-hand side. So the right-hand side, well, you can of course apply the same equation for not degree D, but degree D1 and the D2 respectively. So this C1 has degree D1 and the C2 has degree D2, and see what's going on. So this will be phi D1 plus the dimension of the full linear system D1 H minus the locus where this the dimension. So I want to write down here the delta function for the locus where the C1 for the closure of the locally closed subset swept out by this C1 and degree 1 curves. So let me just write this way. It's delta C1. And this is and then you have another term, which is phi D2 plus dimension D2H minus delta of C2. Okay. And then if you stare at the left-hand side, you see that this term. So you know that if you look at, instead of the modular space of degree D, you can consider the modular space of degree D1. And you know this kind of thing will be bounded by the Severin equality. So the delta C1 will be bounded by the codimension of the corresponding stratum. So then this tells you this is a lower bound. This is the classical Severin applied to MD1 and MD2, the smaller spaces. And then you get, this is phi D1. And that this will have a lower bound, which is just the dimension of the locus of such C1. And similarly, you have the phi D2. And then you have the dimension of the locus swept out by degree D2 curve C2. And then, since the general point of Z is of this form, then the sum of these two terms will just be dimension Z. And then you still have these two terms, phi D1 plus phi D2. Okay, then we are good. Yeah, you just combine this and this. You see, then the left-hand side. So combining both sides, combining both equations. You get the upper bound for delta Z, where of course, you will see the codimension of Z, which is given by dimension B minus of the dimension Z. So you have one term, which is the codimension Z. But this phi D will show up, as I claimed. This is the phi D minus I phi di. So the more non-integral these curves are, the worse this term is, and the more this the Ngo support inequality will be violated. And so that's the full proof of the statement. Okay, so of this claim, and which immediately implies theorem A, combining with the Ngo support theorem. Okay, so let me make some remarks to conclude today's lecture. So the remarks is, so this observation that we look at, well, I mean, the idea of looking at these correction terms and to conclude the no support which will show up outside the integral locus, this idea, so this observation is essentially due to Chaudois-Lemont. Who applied this to Higgs bundles with poles, or twisted, let me just say twisted Higgs bundles and with co-prime rank and degree. And then later, this co-prime condition was removed in the work with joint work with David Schmolik, and also we generalize this to other. This just generalize this to. So the purpose for removing this condition is to prove the kind dependence conjectured by Yukinobu and by Piri-Busu. In particular, this implies that. Just let me finish the sentence and conclude. So this implies that the kind dependence phenomenon for Del Pezzo surfaces for Del Pezzo or Fano surfaces and the cohomological kind dependence, which is rooted in Donaldson-Thomas, the cohomological Donaldson-Thomas theory, is a classical statement. And a consequence of the support and goal support theorem. And then, of course, and the general the last remark is that for now, okay, for Hitchin system of GLN, so this is sort of the Calabi-Yau-2 situation. Kinjo and Koseki prove the kind dependence by using a vanishing cycle argument, reducing to the theorem A, by reducing to essentially to theorem A prime, the full support theorem. And so the statement is the following: if you consider BPS cohomology of the modular of Higgs and D, the rank n and any chi, so this is together with the perverse filtration, so the entire package is kind dependent. But it is no longer the intersection cohomology. This is Kinjo-Koseki theorem. Okay, let me stop here.